In this session, I'll discuss the particle physics and accelerator. This is the last topic. I'll discuss the structure question related to this topic. So in question one, a stationary anti-neutron decay by emitting a positron. Explain how energy is conserved in this decay. So we have a stationary anti-neutron is there, and it is emitting out positron. So how we can say the energy is conserved? First, an anti-neutron is there, which is stationary, but then it emit out a positron. A positron is emitted out. So when it release positron, what will happen? Positron is antiparticle, like electron is there. Antiparticle of electron is called positron. So anti-electron is also known as a positron. So how we can say the energy is conserved here? Basically, when the neutron is stationary, the kinetic energy of the neutron is zero because it is not moving at all. But when it produces a positron, so the mass, because neutron or anti-neutron is having a high mass, but electron or positron, they are lighter. So the mass will be smaller. So from what will happen, how it will get the energy? Because initially the sum of kinetic or sum of energy plus the mass before any interaction should be equal to sum of energy and mass after the interaction. So in the beginning, the neutron was stationary, neutron was not moving at all. So kinetic energy was zero, all it was having a mass. But when this neutron breaks into or give out positron, because positron is lighter, so the mass is smaller. So as a result, if the mass is smaller, what will happen to the remaining mass? That mass is actually converted into energy. So the points which you will include. So first thing when we'll mention like neutron or anti-neutron is producing a positron. It means the mass of the product is smaller than the mass of the reactant. And what happened to the remaining mass? That remaining mass is converted into energy. So the points you will include here, that the mass of product is smaller compared to the reactant. And what happened, how the particle get this energy? So the mass difference provide kinetic energy to positron. Then in question 2, the equation shows the decay of anti-neutron decay into proton, positron or anti-electron, and electron neutrino. Explain how this equation shows that decay obeys 3 conservation laws. So we have to check the conservation of the charge. First thing, we'll check the conservation of the charge, then we'll check the conservation of baryon number, and then we'll check the conservation of lepton number. So first, when we check the conservation of the charge, neutron does not have any charge, so that is 0. Proton is having a charge. Proton is like 1 plus 1.6 exponent minus 19, or relative charge we can write here, that is plus 1. And this is but antiprotons. If the proton is positive particle, antiproton will be negative. So this will be -1. The charge of electron is minus, relative charge is -1, but positron will be +1 because it is antiparticle. Antiparticles have different spins as well as the charge. An electron neutrino is a neutral particle, so does not have any charge. So means the charge is conserved. So first we'll check the conservation of the charge. It is same for both sides. Then what we can check a baryon number. Baryon number for each quark. If a particle is a quark, the baryon number is 1/3, and anti-quark it is -1/3. Because neutron consists of 3 quarks, so neutron consists of, the baryon number for a neutron is +1. But this is anti-neutron, so the baryon number will be -1. So that is baryon number is -1. Baryon number for every proton, it is +1, but because this is anti-proton, so this will be -1. And electron neutrinos and positrons, these are leptons, and leptons does not have any baryon number, so baryon number is 0. So this is also, the baryon number is also conserved. Then we'll check the lepton number. Lepton number for each electron, it is +1, and anti-electron is -1. And same thing, electron neutrino is +1 and anti-electron neutrino is -1. So when we check the lepton number, neutron is a baryon, so lepton number is 0. Proton is also a baryon, so lepton number 0. Anti-electron neutrino, like a positron is there, so lepton number will be -1. And electron neutrino will be there, lepton number is +1. So this is conserved in terms of lepton number. So we check the conservation of the charge, then we check the conservation. Even we can check the conservation of the mass as well. The mass will be conserved, charge, baryon number, and lepton numbers as well. So about the baryon number, lepton number, you have to memorize for each particle and antiparticle. In question 2, mesons are produced by a cosmic rays in the Earth's upper atmosphere. In 1940, the observation is there for decays of the muon, and muons were traveling at a speed about 0.994 speed of light. And Rossi found 74% of the muon detected at 1,600 meter reached the bottom of the mountain. The average lifetime of muon is about 2.2 exponent -6 seconds. So they suggested that their observation could explain using idea from relativity. So explain whether these observations are consistent with the idea from the relativity. What is the concept of the relativity? Relativity is like when object travel close to speed of the light, they gain their mass, or their mass increases. So that's why you will find a common term that is about rest mass. Rest mass means like the mass when the particles are stationary. And what is a relative mass? Relativistic mass, not relative mass. Relativistic mass. Relativistic mass is when the particles are moving close to speed of light. Their mass does not remain constant, the mass increases. That we called as a relativistic mass. So Rossi and Hall made observation of the decay of these muons, and they measured the number of the muons reaching the bottom of the mountain and the number of the positron and reaching a position, about 1,600 meter higher up the mountain. So what will happen as the muons will travel closer to speed of the light, like about 0.994 c means it is like a speed of a light, closer to speed of light. So as it is closer to speed of the light, what will happen? The mass will increase. And as a result, when the mass will increase, the particle will take longer time to decay. That's why most of the particle can reach the bottom of the mountain. So here, like muons are produced by cosmic rays. And in 1940, Rossi and Hall made observation of the decay of the muons. They measure the number of muon reaching the bottom of the mountain. So like there's a mountain, how many muons are reaching at the bottom of mountain? Reaching up position 16,600 high up the mountain. So they were comparing like this height is about 1,600 meter. Like how many muons are there at the top and how many muons reach the bottom of the mountain. And these muons are traveling at a speed of 0.994 speed of a light. And they found that 74% of the muon detected at 1,600 meter reaches the bottom, and the average lifetime of a muon is about 2.2 exponent minus 6. Like this is the time the muon will take to decay. After this time, the muon will decay as the muons are consist of quarks and antiquarks. So suggests that their observation could be explained using idea from relativity. So how we can explain this idea of relativity? First thing, that the muons are moving closer to speed of the light, so the mass will not be constant, the mass will increase. So first point, the muon moving closer to the speed of light, the mass of the muons will increase. And as a result, the mass will increase, the decay time will also increase. Like they will take relatively longer time to decay. And when we work out how much time they will take to cover this distance, like this mountain is example 1,600 meter, and these muons are moving at a speed 0.994 c. So speed is equals to distance divided by time. So time is equals to distance divided by speed. So distance which they cover, that is 1,600 meter. And the speed which is 0.994 into 3 into 10 power 8. When we simplify this, this will give us the time it will take for decay. So 1,600 divided by 0.994 into 3 exponent 8. 5.3 exponent minus 6. Okay. So this will be 5.3 into 10 power minus 6 second. So they have to take, like they will take about 5.3 into 10 power minus 6 seconds. And when the particle move closer to this, and practically the decay time, like normally for a muon, what is the decay time that is given, which is about 2.2 exponent minus 6. So 2.2 into 10 power minus 6 seconds, the muon can decay in this time. So what we'll do, we'll find if they take 2.2 exponent minus 6, how much distance it can cover. So distance will be speed multiplied by time if they're moving with the same speed. So 0.994 into 10 power into 3 into 10 power 8 multiplied by their decay time, 2.2 into 10 power minus 6 seconds. So how much distance they can cover? What's the answer for this? 0.994 into 3 exponent 8 into 2.2 exponent minus 6. This will give us how much distance they can cover. So that is 656. So if they were having a normal decay time 2.2 exponent minus 6, they will only cover 656 meters. They are not, the muons, like after covering 656 meter, the muons will disappear, because muons have are particles with a short life, that these particles are not very stable. They disappear and form or give out energy. So if it means that there is a relativistic effect, whenever relativistic effect is there, it means that as the muons are moving closer to speed of the light, the mass of the muon increases. And as the mass increases, so they will take longer time to decay. As they will take longer time to decay, they can reach the bottom of the mountain. So this is also an evidence that when the particle move closer to speed of the light, they don't have the constant decay time, or their mass is not constant, the mass also increases. After muon were discovered in 1936, they were known for many years as mu mesons. Explain why mu muons are not described as explain why muons are not described as mesons in the standard model. So what is the reason for that? Why muons are not described as a mesons in the standard model? Because what are muons? Muons are lepton, because in a standard model, the particles are divided into two categories. One is known as a quark family, another one is known as a lepton family. So muons are actually leptons, and muons are the fundamental or the elementary particle, the basic particles are there. But mesons are made up of quarks. Because in a standard model, there are only 12 fundamental particles, which are divided into two categories, quarks and leptons. Quarks can be up, down, top, bottom, charm, and strange. And leptons can be electron, electron neutrino, muon, muon neutrino, and tau neutrino. These are the standard particles. Any particle other than this is not the standard particle. So standard model, we have either a quark family or a lepton family. So they are saying after muons were discovered in 1936, they were known for many years as mu mesons. Explain why muons are not described as the mesons in a standard. Because muons are what? Muons are fundamental particles. Fundamental particle means every particle, like they cannot be further divided till now. So they are fundamental particles, and fundamental particles can be lepton or a quark. Why they are not described as a meson? Because what is the meaning of a meson? Meson means it consists of the particle and antiparticle. So when particle and antiparticle combine, we call them as a mesons. But muons are not, they are the basic particle. It consists of only one type of particle. That's why they are not categorized as meson in the standard model. In question 3, in 1937, scientists in University of California use a high-speed particles from a cyclotron to produce isotope of phosphorus. This isotope can be used in treatment of the cancer. So what is the concept here? This is a cyclotron. We produce a particle, then we deflect by magnetic field, then accelerate, then deflect, then accelerate, deflect until it reaches a certain speed and it will come out at a high speed. As a result, when it will move at a high speed, it can collide with other particles and produce other massive particles. Explain the role of electric and magnetic fields in the production of high-speed charged particles in a cyclotron. What is the use or the purpose of electric field? Electric field is mainly used to accelerate the particle or increase the kinetic energy of the particle. And here we apply alternating potential so that we can accelerate between the D's. So particle is only accelerated here, like between the D's, this part it will accelerate. Same thing here, the particle will only accelerate in this part. And there's always an alternative terminal, like when the particle is moving from one D to another, like these are the two D's. If the particle is moving, the particle we use a magnetic field to deflect, then say positive, negative, so particle will accelerate here. When particle enter and deflect again, then there will be again opposite terminal, so it will accelerate. So every time it will receive the same like polarity or same terminal of the battery, so that it will accelerate between the D's and it will deflect. Eventually it will come out from the D. So here electric field is used to accelerate the particle and increase the kinetic energy. So we can use the electric field to accelerate the particle, or we can use it to increase its kinetic energy of the particle by applying alternating voltage. Then what is the purpose of a magnetic field? The magnetic field is used to deflect the particle. And magnetic field is applied perpendicular to the motion so that it can deflect the particle and particle can undergo a circular motion. So in a small space, we can move the particle to a greater speed. So magnetic field is applied perpendicular, because if you apply parallel, it won't experience the force. The magnetic field is applied perpendicular to the direction of the motion of the particle, which rotate the particle and as a result, the particle can be accelerated to higher speed in a short space. So this is always the case, use of electric and magnetic field in a cyclotron. In second part, the cyclotron could produce a beam of alpha particle with a kinetic energy up to 16 mega electron volt. Calculate the magnetic flux density which is required by the cyclotron when alpha particle with a kinetic energy of 16 mega electron volt are produced. The diameter of a cyclotron is 0.94 meter and mass of alpha particle is 6.6 into 10 to the power minus 27 kilogram. So first, using the kinetic energy, there's a relation like when particles are accelerated using a kinetic energy, like using the electrical energy, we accelerate the particle. So, and there's a relation between the circular motion and the magnetic field. Like here, when particles are accelerating, the kinetic energy is due to electrical Ke is equals to electrical energy. And when object is moving in a circular path, we can say centripetal force is equals to magnetic force if we are using a magnetic field to rotate the particle in a or move the particle in a circular path. And here we have mv square over r is equals to qvb. So we will cancel with square. So it is mv over r is equals to qb. So this is a formula which we can use to work out, as we want to calculate the magnetic flux density. So we need B, where m is the mass of the particle, which we have. R is the radius of the curved path. That will also be there, because if we know the diameter, we can have radius. Then what we need the speed. So how to work out the speed? As we assume the kinetic electrical energy is used to accelerate, so electrical energy will be equal to kinetic energy. Or there is also another formula which relate the kinetic energy with the momentum, that Ke is equals to because kinetic energy is half mv square. If I multiply and divide this equation by m, so it will be half m square v square over m. So the formula in that case, Ke will be equal to p square over 2m. We can also use this formula to get the momentum, and from momentum we can find the speed. But any one of the formula you can use. So kinetic energy is equals to electrical energy, but the kinetic energy is mega electron volt. Electron volt is not the SI unit. So you have to convert this mega electron volt first into joules. So first we'll convert this mega electron volts into joules. So 16 mega electron volt, first we'll convert into electron volt. Mega means 10 power 6, so it will be 16 into 10 power 6 electron volt. Then electron volt we want to convert into joules. So 1 electron volt equals to 1.6 into 10 power minus 19 joules. So if we have 16 into 10 power 6 electron volt, this will be x joules. We cross multiply. So electron volt we convert into joule by multiplying with 1.6 into 10 power minus 19. So the energy what we'll get, this is 16 into 10 power 6 times 1.6 into 10 power minus 19. That answer will be in joules. After getting this answer in joules, use the formula kinetic energy is half mv square. So kinetic energy we have now, mass of the alpha particle is already given. So we will work out the speed. 2.56 exponent minus 12. Okay. So this will be 2.56 into 10 power minus 12 joules will be there. Then it will be 1 by 2. M is the mass, which is 6.6 into 10 power minus 27. And v square. So this 2 will be multiplied 6.6 exponent minus 27, then take a root. After taking a root, you will get the value for speed. And then we have the original formula mv over r is equals to qb. So we need the b. So it will be mv divided by rq is equals to b. M is there. That's already given. V we already worked out. R is the radius, which we can find from its diameter. Diameter divided by 2 will get the radius. And Q is the charge of alpha particle. Alpha particle consists of 2 proton and 2 neutron. So the charge of alpha particle will be 2 into 1.6 exponent minus 19. That is the charge. So we'll have Q, R, V, M. So just substitution and we'll get the value for P. Is it clear? In question 4, a section from a periodic table is shown. So technetium, which is Tc produced when deuterium ion collide with the nucleus of one of the other elements shown in the table. In this process, number of neutrons are also released. The deuterium is an isotope of a hydrogen which is having 1 proton and 1 neutron. Complete the nuclear equation to determine the element and the number of the neutrons which are released. So how we can work out this? Because the mass should be conserved, the proton number should also be conserved here. For hydrogen, 1 proton, and nucleon number is a sum of neutron and proton. So this should be 2, because 1 proton and 1 neutron, so 1 plus 1 it will be 2. So total on this side, 9 plus 2, so 98. So here we have 5. So how many should be there? Because on the left hand side it is 98, so right hand side should also be 98. So that's why we put 3 here, because 9 plus 2, 98 on the left, and 95 plus 3, 98 on the right. Then at the bottom also, neutron does not have any proton number, so that is 0. So on the right hand side it is 43. So on the left hand side should also be 43. One is here, this should be 42. So which element is 42 MO? That is 42. So this is the complete equation. And how many because one neutron, for each neutron it is one here. So how many neutrons should be released? 3 neutrons should be released. Because 96 plus 2, 98, and this is 95. So each neutron is one here. So how many neutrons should be released? 3 neutrons should be released. So the sum will be 98. So this is a full equation. In question 5, the following passage is taken from article about the history of the particle physics. Mystery particle. In 1932, scientists knew the existence of subatomic particle, the electron, the proton, and the neutron. These were believed to be a fundamental. As you have studied, like when you were there in class 7 or 8, you have studied the Dalton atomic theory, and there it was written that atom is an indivisible particle. So that time atom was considered as a fundamental particle. But after the discovery of neutron, proton, and electron, they consider that neutron, proton, and electron are the fundamental particles. Were the fundamental. But then in 1936, scientists were using a track of cosmic rays to identify a predicted particle known as mesons. Instead, another particle was discovered. So actually, they were checking the track of a meson, and from mesons, they identified another particle, muon. And this was so surprising that the Nobel Prize winning physicist describe how the underlying particle fit into the standard model. So how this particle muon can fit, muon and mesons are fit into the standard model. And here we have electron is there, proton is there, neutron. These are the underlying particles. So first, just you have to write the statement about these particles. First, electron. So what is electron? Electron is a fundamental particle, and it's also a first generation particle. First generation particle means the particle which was discovered early are known as a first generation particle. The particle discovered after like mid 1940s, 1930s are known as the second generation particles. So first we have electron. You just have to write the description of each of them, how it fit into standard model. Electron is a fundamental particle. And it belongs to lepton family in the standard model, because standard model divide the particle into families lepton and quarks. So electron is a fundamental particle and it belongs to lepton family. Then what about neutron? Neutron is not the fundamental particle. Neutron is actually a baryon which consists of 3 quarks. Baryon means the particle consists of quarks. Quarks are fundamental, but neutron and neutron and protons are not fundamental. Then we have proton. The same description, it is not the fundamental particle, it's a baryon and consists of 3 quarks. And quarks particles are fundamental. Then we have mesons. Mesons are not fundamental as well. They are consisting of quark and antiquark. Like one quark is there and another anti-quark is there. And the last one is muon. Muons are fundamental particle. They are leptons. Which experience a strong nuclear force, weak nuclear force. Quarks experience a strong nuclear force. So just the points which you have to mention. Neutron protons are baryons. Baryon means which consists of three quarks. Meson is not a fundamental. It is a combination of quark and antiquark. Electron and neutrons are leptons, or you can also mention neutron, proton, and electron are first generation, where muon is a second generation particle. And leptons, electrons, muon, quarks, these are fundamental, where proton, neutron are not fundamental. Then another question, in 1908, Rutherford, Giger, and Marsden investigate the interaction of alpha particle with matter. In one set of experiment, they directed the alpha particle towards a thin gold foil. State why alpha particle state why the alpha source and a gold foil were contained in a vacuum. So why we have a vacuum? Because if there was no vacuum, then the particle may collide with the air molecules and they might lose their energy. So air does not stop the alpha particle. That's why there is a vacuum. So why we create a vacuum? So the air particles does not stop them.